Okay, so in the previous lecture, we look at FSK, especially on Synchronous FSK. So before I move to PSK, there's additional concept of Synchronous FSK in our syllabus, or coherent FSK detector. So we continue with this Synchronous FSK receiver before PSK. So with Synchronous FSK receiver, we'll multiply our VFSK with the carriers. So we have two carriers, right? One frequency to carry one carrier frequency to represent bit 1, and another carrier frequency to represent bit 0. Okay, so we'll multiply our VFSK with both, both frequencies. Okay, and then we have this summer that sums the top output from the top with the inverted of the below's output. Okay, so whatever that we have output here, you minus with the below output. Okay, so our VFSK can be either in two forms. Can be, if it's bit 1, what we receive is EC cos omega C plus delta omega T. If it's bit 0, it's EC times cos omega C minus delta omega T. Okay, so from the amplifier, and the summer amplifier here, will receive the DC voltage. Okay, if we receive this one, the first signal output from the amplifier, we can try just using the normal trigonometry identity that we have used before. So this is the output that we get at here, over here at this point, VDT. Okay, if we send number 1, we'll get number 2 over here at this point. And then the LPF will stop all the higher frequencies. Okay, and then it's left only with this part. Okay, EC over 2. Okay, if we're transmitting this number 3 that represent bit 0 at VDT, over here you'll get number 4, number 4 signal, and after LPF you get the minus EC over 2. So this positive voltage will be translated into bit 1 and negative to bit 0. Okay, okay, let's try one of the, and this is the probability of error for synchronous FSK. So it's half error function square root 0.5 EB over R naught. Okay, so let's try. Okay, let's try one input, which is the positive input. Okay, so if it's bit 1, then what we get from as our VFSK is EC Okay, in this example, I just show for bit 1. You can try yourself for bit 0. You see cos omega C plus delta omega T. Okay, and then we'll multiply this one and with our local carrier, which is cos omega C plus delta omega T. So this is from the top arm, and then minus the same signal is C cos omega C plus delta omega T. Okay, so this is our FSK multiplied with the below arm, which is cos omega C minus delta omega T. Okay, remember our diagram, we have this VFSK, yeah, which multiply with here is the yeah, this one is carrier frequency for our bit 1 cos omega C plus delta omega. This one cos omega C minus delta omega. Okay, and then we will sum this one plus about below minus, and we have the LPF. Okay, so when you solve this, what you get is okay EC cos square, right, omega C plus delta omega T minus EC. So this one can use cos A cos B identity. Okay, and then here we solve, we got EC over 2 plus EC over 2 cos 2 omega C plus the omega T. Then for this part, we got minus EC over 2, okay, cos 2 omega CT minus EC over 2 cos 2 delta omega T. Okay, so here you can see these are the DC voltage and all the higher frequency components. Okay, so after LPF, okay, we have only this EC over 2. Okay, and then this EC over 2 is positive voltage that we translate into bit 1. Okay, okay, so this is for example to solve the mathematical part for synchronous FSK. If our VFSK is equal to EC cos omega C plus delta omega T. You can try yourself for bit 0, which is cos omega C minus delta omega T. Okay. Okay, let's go back to our slide. All right. So let's try the same example here, example 5.2. Okay, the question asks us to calculate bit error rate for FSK, synchronous FSK, and compare with the previous that use a synchronous FSK. Okay, from the previous, what we got is our EB is equal to 4.545 millijoule, yeah, and our N naught is equal to 2 times 10 minus 4. Okay, so and the equation for PE for the synchronous FSK is half error function square root 0.5 EB over N naught. Okay, so if we solve and put this EB and N naught inside this equation, you will get half error function 3.37. Okay, so if you look at the table, okay, you can refer to the table that I shared in the Google Classroom. It's around 1.52 times 10 to the power of minus 6. Okay, from table, one point 1.52 times 10 to the power of minus 6. So this is equal to 7.6 times 10 to the power of minus 7. Okay, if we use equation, okay, we can use this equation because the x here is quite it's larger than 2. Yeah. So if you use equation, error function x is equal to, here I just put x is equal to 3.37. So error function 3.37 is equal to exponential minus 3.37 square divided by pi, square root of pi times 3.37. And if you solve this, you get around 9.8 times 10 to minus 7. Okay, so you can notice the difference here between table and equation. Here, it's around 8 error bits per 10 million, and over here is 10 error bits over 10 millions. Okay, but in terms of the order of bit error rate is similar, which is 10 to 7, or 10 minus 7 here. Okay, so 10 minus 7 is just over here, there's slight difference, 8 and 10. Okay, so that's for the synchronous. Okay, I'll stop first.